All right. So this is what I want to get at today. Darn thing, man. Darn it. All right. Okay. So let's get to what we're getting at here. We can get rid of Desmos. Oops. For now, I might need to do a Desmos tutorial with you at some point. You know, tomorrow. Okay. So there's something I want to explain on slide 2, and this is going to be kind of the lecture for us today. Okay. Since you've done the lab work, is that all in the lab she wanted? If that was it, then okay, good. Now what I want to do, go to slide 3, and what I'm going to do first is I'm going to explain to you really cautiously. Um, Let me go a little closer. There we go. Really cautiously, what orbitals are and what electron, am I saying that right? Electron configuration is. Um, Let me do this real quick. That should be sufficient for me. Now, I'm not going to go into like advanced Vesper here. Valence electron repulsion theory, blah, 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 blah. We're just doing the basics. And so I'm going to explain it in a very basic sense, okay? What is the deal here? You need to work for me. There we go. So I want you to notice something when you look at these. Do you see this 1s1 for the hydrogen atom? You see that? So when you got something like I'm going to discuss electron configuration. We'll do sig figs and stuff in another lecture because I want to keep it interesting. What do we mean by 1s1? What that means is you've got one electron for hydrogen, so we write 1s1. But what does s mean? That's the orbital that you're occupying.
So does S mean solid?
No, not in this. Not for this. This is electron configuration. So I'm going to write that out. We're doing electron configuration today. If it was solid, we would put parentheses beneath the element. But that's not what this is. We do little bracket and that. And so that means that you've got this energy shell, okay? The spherical energy shell. We're not going to do the negative orbital, even though it exists. And that means you've got one electron. And then the way we write that out simply, and you don't have to do this yet, but we'll put that shell there. We'll put that for that one electron. But it actually doesn't have a neutron. Just looking at the periodic table, I can tell that because the atomic mass is 1. And I'll get to that at some point in another lecture. And your atomic number is 1, which means you don't have. That means you only have one proton. No, if it was a neutron, you'd have 2. But the point is electron configuration. When we get to something like helium, then we've got 1s2. So you're in the first energy shell, right? But you've got 2 electrons. And usually that occupies positive and negative, right? But I'm just going to keep that kind of on the 0 there to kind of show that you got 2 there. And the way we would write that out, now looking at the periodic table for that one, go all the way across and you've got, notice how you've got 2 protons and 2 electrons. Okay? And I'll write that out. But you also have 2 neutrons. And usually that's how it happens. You'll have 2 protons and 2 neutrons because it's got an atomic mass of 4. But I'm just doing electron configuration. Let me do this. So 2 protons 2 neutrons. Do you really need to do the protons and neutrons for this right now? No. When I do the electron configuration, you just need to know that that number 2 for helium up on the periodic table to the very right, it's that you see that number 2 right there. That's its electron configuration, and it's in the first orbital 1s2. You get me? Now, this is where it's going to make sense. When you bump down to lithium, that's going to be 1s2, 2s1. So why am I putting a coefficient 2 in front of that? Well, that means that you've got another orbital. And I'm not going to keep doing the protons and neutrons because that's not about electron configuration. You do the electrons. So your first shell is there. Your second shell is there. Does that make sense? And in the second shell, you've got one extra electron. How do I know that? Look up at lithium. You see that number 3?
Yes.
But why did I put a 2? When you go down the periodic table, you gain another energy shell. So the first row is 1. The second row is always 2. Make sense? And as you go across, if it's the next element in line, you pick up another electron. So if I did beryllium, right? It'd be 1s2. And you guessed it, 2s2. And it would look something like this. 2 electrons there, 2 electrons there. Making sense? I don't need to do the rest there. That's Vesper. We're not going to worry about that stuff, and we're not going to worry about protons and neutrons yet. We're doing electron configuration. Now, if you go to boron, so here's the thing. When you get to the right, when you skip all the metals and you get to that number 13 column there, right? Then it's no longer just the s orbitals, but it's still in the second energy well. So yes, you'd still have 1s2, 2s2, but now you have something that I'm about to introduce that is new, 2p1. So the p means that you can only have 2 electrons in each s orbital for the alkali metals and alkali earth metals, okay? But once you get to when you skip all the metals, you skip them because you're in the second row. There's none in the second row. Then you get to boron, and we have to use something different because you can only have 2 electrons per s shell. So we've already maxed all the s shells for row 2. So then we add something called p. So what you might do is you just write that out like this. You need a third circle. So the outermost shell is your p shell, okay? As far as organic chemistry is concerned. Then we put that extra electron. Notice how boron had 5. There's 5. Beryllium 4, lithium 3, helium 2, hydrogen 1, right? Now I'm going to skip a few. Right, I'm going to go all the way. I'm just going to go to fluorine, okay? Do you see the periodic table? You see the numbers? Do you see what's cool about the periodic table? Is that it includes your electron configuration. I'll let you know, Z, they don't, they never include the electron configuration in periodic tables. The one I'm providing to you, I bought and has them, right? So let me explain something to you. I'm going to put, now that we're here, I'm going to show you on the periodic table down here. You see this? You see that right there? You see the boron? You see how it says 5? So notice how that's 2s2, 2p1, right? There's a 1s2 there. They just don't put it because I'll explain that later. But they'll give you the outermost shells. Notice how carbons is 1s2, 2s2, 2p2. Look at that. It just went up another, didn't it? Notice how nitrogen's is 2s2, 2p3. It went up another. 5, 6, 7. Notice how oxygen went to 2p4. It went up another. Notice how fluorine's is now 2p5. Neon now 2p6. Once you get to 8 in the outermost shell for 2, you're done. So why is there a 10? Because 2s2, 2p6 is the outermost shell. What do I mean? Well, we know we're in the 2 sets. And we have that 1s2 in there. We're just not including it because they're only including the rows outermost shells. So the outermost shells are the 2s2 and the 2p6. Technically, this is done by just absorbing these two shells into one shell, right? But we'll get to that later. But for now, this is how they are. 2p6, 2s2. We don't include the 1s2, even though it is included. I will, for the sake, the periodic table doesn't, but because it starts from the previous row, assuming that those electrons are maxed out, which means they're still there, we're just not writing them. But you've got 1s2. How do we know that it's 10? Because you got 2 electrons here, you got 2 electrons here, and you got 6 there. 2 plus 2 plus 6 is 10 for neon. Does that make sense? So for carbons, 1s2, 2s2, 2p2, for a total of 6. 2, 4, 6. For nitrogens, 1s2, 2s2, 2p3, for a total of 7. 2, 4, 7. Makes sense? Okay. And that's how we layer it. Now, if we went down one more row, and I'll quit it for the day, but if I went to, let's say I went to sodium, right? Well, that went down an extra energy level. Technically, you say up when you go down, but it means we gained an extra energy level, that being 3. So if neons was 10, then I would write 1s2, 2s2, 2p6, and I know I'm at neons, right? But if I go down to, if I proceed to sodium, now it's 3s1. So I got 10 here, that was neons, but I gained another. That's what that 11 means on sodium down there. So sodiums would have an atomic number of 11. And so then that's just electron configuration right there. So if you look at the periodic table, that's exactly what it should look like. You should see that 11. And I'm going to explain something real quick before I continue so we understand why it's not including the other ones before it. So why is it putting neon and then 3s1? I'm going to ask you. That's your question for the day, and we'll call it. So why is it putting neon bracket 3? I thought it was sodium. Why are they putting neon 3s1? Well, let me ask you, what's the electron configuration of neon? That's why. They assume that you know that 1s2, 2s2, 2p6 is neon. And when you're in the new row, it makes it convenient to write out. That way you don't have to keep writing this. You already know that it's assumed that that's neon. So we just write the electron configuration. We just write neon out instead of doing all of that. We already know it's that. And so we just put neon 3s1 and we know it's sodium. Does that make sense?
Yeah.
So once you go down the other row, you always use the noble gas to tell you what its previous electron configuration was. That way you're not having to write the whole thing for sodium. Does that make sense?
Right. Thanks a lot. Thanks, National. Sorry.
You're good.
So thanks a lot.
Anakin, Chancellor Palpatine is evil! From my point of view, the Jedi are evil. Well, then you are lost!
Ninja!